Excellent. All right. Hello, everybody. Thank you for tuning in here for Ether Roundtable number 47, maybe 48. Thank you so much for being here. And tonight we have a presentation from Alan. So this should be pretty awesome. The topic tonight is kinematics, dynamics, invariance, and covariance, as you see on the screen here. And so, yeah, without further ado, why don't you go ahead and take it away, Alan?
Thank you, good sir. So yeah, this presentation was sparked by a debate that Wits had last Sunday, where they got into a situation where they were talking about kinematics and dynamics, like the dynamic cause versus just a description of something happening, right? And what it came down to was his opponent kept deriving onward acceleration without a causal mechanism and was like, look, I derived it. And like that was Witset's entire point. And this is kind of lost on mainstream. They kind of teach the two with no distinction now. And we'll get into the reasons why they do that here. But this is to break down the specifics between kinematics and dynamics, invariance and covariance. All right. So all the references are available here on Ether Cosmology or get.ethercosmology.com/Alan/Zotero. Click find file. And from there, you can search the title of anything that's referenced in the presentation. And if you want the whole presentation to see what was referenced, go to my Obsidian, which will be in the will be in the description, and you can search the references there, and they're all available here. All right, so we're going to start us off with Shankar's introduction into kinematics and physics. What he tells us about the two is the following. Kinematics and dynamics. Kinematics is the complete description of the present. It lists what you know about a system right now. For example, if you're talking about a piece of chalk and you want to know where it is and how fast it's moving, that's kinematics. Dynamics tells you where the chalk or why the chalk goes up and why it goes down and so on. It comes down due to the force of gravity. In kinematics, you don't ask the reason behind anything. You simply describe the things the way they are. Dynamics tells you the how and why of the description and why it would change over time. The equations that govern kinematics are as follows. Right, these are pretty basic. What they're all describing is just change in position over time with respect to a velocity that's either constant or an acceleration, and then you can take derivatives of that to figure out how much the object would be displaced over X amount of time based off of its acceleration or what have you, right? And there is a graphical error here. This is supposed to end in t squared on the equation number 3. And then I think that just bugged out or something. So 1 second. Okay. Sorry about that. Oh, word. Oh. Oh. Okay. So just to kind of add on to what we were just talking about there. So say you have a ball and you drop it. Well, you can use those equations to find out how much acceleration the ball is experiencing at X amount of time, where it'll be displaced in accordance to the height where it was dropped, or how much or how fast it'll be traveling when it hits the ground, etc. Right. So those are the kind of things that you can use that are just based off of measurements. Kinematics is measurement with no regards to causal mechanism, and dynamics is all about predictions of future motion, explicitly accounting for causal mechanisms and forces. Okay, so to kind of reiterate that, we have the chapter 1 intro to the principles of dynamics. The principles of dynamics are a subset of mechanics that deals with bodies in motion under the action of forces. Here we have the summation of force equals mass times acceleration in some direction. And to get to the study of dynamics, we must be able to handle correct force analysis. So when you get into making future predictions of motion and assessing what forces are going to be relevant to your predictions and whatnot, that's where you're going to get into force analysis and what applies to what situation. They give a couple examples here. So before we had a ball that was dropping and we had a height and we had a time. We were seeing where the ball would end up, at X amount of time based off of its motion, right? So here in the examples now, we have forces that are acting on particles, and now their prediction is going to be where this particle is going to be based off of its current momentum, and then the other forces acting on it. That's the difference. And then there's just another iteration of that, future predictions of motion based off of force interaction. All right. covariance and invariance. Oops, that's supposed to come later. Sorry about that. But yeah, so kinematics and dynamics are two important parts of physics, two branches of physics. And in that, the whole of mathematics of physics is governed by covariance and invariance. Now, invariance is just a fancy way of saying that you're preserving the laws of physics under transformation. And covariance would be your preserving the laws of physics under transformation, but the coordinate systems that you're using are changing in a predictable way to facilitate the constancy of the constant that you're transforming. So in the example of like special relativity, a real easy one would be the speed of light being c. When they do the transformation to the moving reference frame, a frame's going to experience length contraction and time dilation as a function of the square of the velocity over c squared. So what that means is they're just like it's a predictable change to the x coordinate and the y coordinate to facilitate a constancy of c. So it'll make c, invariant under transformation, but it's only supplemented through covariance where we have a predictable change in the coordinate system. Okay. So when we get into kinematics and dynamics, a big aspect of what we see going on in the sky is associated with being correct with Newton's laws and all these things, right? And mass attracting mass is the dynamic force that's causing these bodies to move, which produces a velocity, etc. So when you get into the backbone of that, we see that Kepler's laws are backwards compatible with Newton's laws and vice versa. So we'll take a look at the start of Kepler's laws, which is just kinematics. We have Kepler's first law is that a planet on an orbit is on an ellipse, which has two focal points, which is just defining the geometry of an ellipse, for where you're going to be aphelion and perihelion. So you're going to be going slowest and fastest on your orbit. So he's just defining the geometry of that. His second note is describing the aphelion and perihelion velocity shift. That's what it looks like in their model. And we have this third law that the square of the orbital periods of the planets is directly proportional to the cube of the semi-major axis of their orbits. So when you're watching planets go complete an orbit in the sky, you're taking measurements of how long it takes for it to get back to its original spot when you first started the measurements. So over the course of a year, when you're looking at the sun, you would be looking at waiting for the sun to return back to its elevation angle of when you first measured it, and that would complete one periodicity. So through that mathematical extrapolation and using a constant ratio or turning velocity into pi to give it an orbital diameter, all of this is just derived off of empirical observation. There's no dynamics involved in it. It's all just ratios of constants and periodicity. So when they introduce Newtonian mechanics to it, there's the mass cancels out in the equations, and actually supposed to have a little mini thing to show for that. Second. All right, so a second. Sorry about that. Okay, had a phone call interruption. So when you take the mass of these equations, right, what they started with was with Cavendish to get their measurements to even start applying these equations to put them in the sky to make them backwards compatible with what Kepler did. What they did is they started off with Cavendish, where they came up with a ratio for the gravitational potential between the two balls, and then they came up with a way to God damn it. Fine, thank you. Good.
Dude, that's unlucky timing.
After this, we should have quick questions because this is a super important facet, and I think everyone should ask questions on it.
Well, while Alan is taking his phone call, maybe I should just say quickly that the gravitational constant G was really in the late 19th century where they kind of isolated it out. But there were great mathematicians like Laplace and Gauss and Euler, who, when they did their celestial mechanics in the early part, or the late 18th and early 19th century, they would use ratios. So they didn't really explicitly use the big G, because they that really didn't come in vogue until the late 19th century. So it's just interesting that they used ratios and avoided the use of big G.
That is super interesting, because our argument is that they only ever needed ratios. Interesting
Yeah,
point, Eric. Wow.
yeah, sorry about that. I apologize for the interruption there. One's echoing. Yeah, thank you, Eric. But yeah, so they established the lore right through Cavendish, and then they committed to these constants, and then they use these ratios of these constants now. So Cavendish gave them the mass of the Earth, because you can algebraically work out what it would be to provide the gravitational potential for those two balls to do their thing for the Cavendish experiment. So when they did that, they got the mass of the Earth, and then just measuring, or just waiting for the periodicity of the sun going around in the sky, they were like, oh look, if we invert this algebraically, we could now figure out what the mass of the sun would be, right? So all they did is they established a new set of constants. So now they apply all periodicities of planetary motion with respect to, how long it takes for it to complete its orbit, and then that ratio just gives them what the mass would be of the planet, right? And then you could do the same thing with, say, Jupiter and Jupiter's moons. Once you have the mass of Jupiter through doing the same thing, its periodicity, just watching it on from your position on Earth. Now that you have its big mass, now you can apply this little mass to its moons and the periodicity of their orbits, and then suddenly you have their orbital, size, weight, and how far away they are, et cetera, right? With all proportional scaling, because that's what this whole system does. This is why this graph looks linear, even though the distances apart are insane, because it's just based off of the periodicity. So as the periodicity gets longer, the quote unquote distance between the object and the sun, gets longer or gets bigger mathematically.
Now, would
That's
that be
that's all
covariant scaling right there?
that's all we're looking at there. Yes.
Right.
So what happens if you put the mass back in, you might ask, because people will argue, well, it's just it algebraically cancels out, but when you put it back in, when you solve a Hamiltonian, when you throw salt behind your shoulder and turn around 3 times and click your heels, the mass, it'll change it. Well, when you do the example that I just gave about Jupiter and its mass and how they would cancel out for the periodicity of the moons and stuff, when you put the mass back in, it changes it by 0.1%. So it's not relevant at all. You would never know. This is all based off of ratios of constants and periodicity of events. That's entirely kinematics, right? There's nothing dynamic about any of this. The fact that you can use a constant of what you're saying is mass, of like how much something weighs, and then in relation to its gravitational potential, right? All these constants were supposed to provide that dynamic explanation, right? This mass attracting mass produces a velocity of 30 kilometers a second. That's why
Right.
the experiment of Airy's failure, Arago, and Michelson-Morley were so important, because this dynamic cause of inherent mass it wants to just come together, right? It has to produce some velocity, and that's how they came up with everything, because all this proportional scaling would dictate that the Earth has to be moving at 30 kilometers a second, so that in 1 year from now, 365 days or thereabouts, it'll be in this exact same spot. So everything in the sky will look accordingly.
It's crazy, how can mass be the dynamic cause when the form that you're using there is mass entirely like gone? And so if it was a dynamic cause of anything, we wouldn't be able to do anything that I showed. Like that wouldn't be the basis of everything.
Yep. Then we went over Cavendish a little bit. I kind of got ahead of myself. Yeah, so for Cavendish, they were just establishing that same ratio with two lead spheres. Now they said, okay, well, we discharged all the static electricity and whatnot from it. So any possible reason that these balls oscillate, we're going to attribute that deviation angle to the torque of the gravitational force of the Earth in relation to the weight of the Earth. Oops. And we have all the equations for that. So G equals M1 times M2 times tau over R squared. So all this is the weight of the balls. So how do you get weight? Downward acceleration. You just it's all the same thing. It's always been a ratio of the acceleration of when you drop something. Nobody knows why things fall or why nobody knows. Right? It's just asserted through this measurement that the causal mechanism is mass, and there's the ratio they gave for this, and then they applied it to the sky, and they were like, "Oh, look, how could it not be? How could the Earth not weigh this much, et cetera, right?" Um, yeah, they get into, just to reiterate the laws again, it's all kinematics. There's nothing about this is dynamic, and the fact that you can interchange Newton's equations with it doesn't add any more explanatory power in terms of a causal mechanism as to why a body moves in space. Okay, and we think we covered the interactive pres part already. So when we so they have all this set up, they've got their ratios, they've got their mass, they know how fast everything is moving in accordance with its distance and its mass in relation to the sun because of that attractive force between them, right? So when they went to start measuring the velocity of the Earth or coming up with ways that they could substantiate the velocity of the Earth, they started off with Arago. Assume that he would have to change the focal length of his telescope 6 months throughout the year because you're going towards the stars and then you're going away from them based on your orbit around the sun. And what he found was that he didn't have to change the focal length at all. The second test was to half cover his telescope with a crystal prism and see if, when the starlight intersected the crystal prism, if he had to tilt the telescope a little further to keep the starlight in the center. And the reason for that is when light hits that refractive index of that crystal, it's going to be traveling slower, and Earth's orbital velocity at 30 kilometers a second is going to move out from underneath it, and it's going to keep the star in the center, you're going to have to tilt it a little further. Let's see what Arago found. As E.T. Whittaker puts it, Arago submitted the matter to test of experiment and concluded that the light coming from the stars behaves in all cases of reflection and refraction precisely as if the stars were situated in place in which it appears to occupy in consequence of the aberration, and as if the earth were at rest. So the apparent refraction of the moving prism is equal to the absolute refraction of a fixed prism. So no velocity component to be found in there. And then we get to Aries. To Airy, it was same premise, but this time they were filling the telescope completely with water. The premise of this experiment was that if the Earth was moving, they would have to tilt their telescope 15 degrees over the course of 6 months, and then they would have to tilt it back by 15 arc seconds over the course of 6 months, and then back 15 arc seconds when you're moving towards and away from the stars to keep starlight in the center when you have a water-filled telescope. What they found is that they only had to tilt so they had a predicted amount of 30 arc seconds of tilt, 1 kilometer of velocity per arc second for a total of 30 kilometers a second. And they only measured 0.8 arc seconds. So fractions of what they had expected. And there's, just another falsification of Earth's motion. The only explanation that was put forward to answer this was maybe there was ether inside of the telescope and it was bouncing around and it carried the light in the opposite direction of the motion, which is obviously incoherent. Then, of course, the other explanation would be if you believe in the quantization of light as little particles, you would have to say that the light accelerates when it hits the water, which is a violation of the conservation laws. Makes no sense. You would have to tilt the telescope if the Earth was moving out from underneath the starlight that was coming into it. So the implication here is that the starlight already comes in at an angle and the Earth is at rest. So these are experiments that are, these are measurements, right? These are kinematics that are falsifying the dynamic cause, right? Because the predicted amount of displacement isn't there. Correspond to the velocity of Earth. Now we take it to 1887 to Michelson-Morley, where they came up with an interferometer to measure the motion around the sun. They had the predicted amount for 30 kilometers, and that would come out to 0.05 of a fringe, and they measured just over 0.1 of a fringe. I'm sorry, 0.01 of a fringe. And that corresponds to a velocity of 6 to 8 kilometers a second. And that's way outside the heliocentric model. So what they did was they rounded that down to a nice clean 0 and said the speed of light must be constant and you can't use it to measure relative motion. And then, so we're looking at some more of the measurements here just to show that they had statistical significance. They weren't not a null, right? They're definitely within the error bar. Any questions so far from anyone?
I just wanted to say that that new Aries failure or Aries success setup is awesome. A little screen you have there.
Oh, that's the old one.
Is it?
It's decent. Yeah.
You drew the telescope and everything?
Yeah. Yeah. And you can even fill out, you can turn off the water, dude.
Whoa.
Now it's the
That's awesome.
Whoa!
Okay, all right, hold on. Where's my applause button? That's pretty good.
Thank you. Got a big budget around here, boys. Oh. So yeah, when it came to interferometry and substantiating the Earth's motion, they kept coming up with measurements that didn't show their predicted amount. It even got to the point where they did an experiment and they got as far as it was like almost 27 kilometers a second. And then they were like, "Oh, you know what though? This is wrong. This must be an error because we know that the velocities amount to thousands of kilometers per second around nebula." So they took their interpretation of the sky and expansion and distances and velocities and masses, et cetera, et cetera. They looked at their experimental data that directly refuted that. And they said, no, what I believe goes on in the sky supersedes the data on the ground. This is a null. So they rounded down their near 27 kilometer velocity to 0 because they could never substantiate it in a meaningful way. For this particular, this is from Kennedy and Thorndike. What these lads had was a asymmetrical interferometer, so one of the arms was longer. That's why it gave a slightly, or a much larger velocity. But that's not how you make the measurements with that type of interferometer. When you do that, you're going to get a disproportional ratio in the readings. So that's why they had to throw out the whole thing anyway. But this whole story of like, well, we know because we assume we're going around nebulas at that. Like, no, that's insane. Okay. The only way that you can get out of this mess is if you introduce second order covariance to bolster the claim of the invariance of C. This is done through the mechanism of special relativity. This is why it was so important for them to redefine all of physics over this, because at this point they gave up on covariance. They gave up on invariance. So starting back with Maxwell's equations, which helped lead to the derivation for the prediction for Michelson-Morley, it had no problem with Galilean transformations not being compatible with Maxwell's equations. It wasn't an issue for them because they all believed in a stationary ether at the time. So it was like whatever for them. It wasn't until they went to measure the velocity of the Earth that they were like, oh snap, we need to fix this Galilean invariance problem. What they did with Einstein introducing time coordinates as partial derivatives, they're able to make second order interpretations of Maxwell's equations that give them the what's called covariance. Right, so it restores motion to Maxwell's equations, but through the mechanism of covariance, meaning the coordinate system changes to supplement the thing in nature that they say is supposed to be invariant. This is a fake version of physics. This is like secondhand, hand-me-down physics. Like this is the mathematical overlay that's been put on top of the world at this is how the magic trick works, right? We've all been down the road where we're like, how can they all be calculating stuff and it not like they're not all in on it? Like what's going on here? Well, they've abandoned actual invariance and adopted Lorentz covariance. And this is done by link contraction and time dilation here. And as you see, it's the amount of contraction you experience and time dilation you experience is a function of the square of your velocity over c squared. These are the quote unquote allowed changes for covariance, right? The amount of changes to the time coordinate and the x coordinate are allowed to happen so that they can make the speed of light the same. So if you need the speed of light to be the same, you use a Lorentz transformation. use covariance to make to give you invariance. What's up?
Oh, is that Einstein's wonderful equation we're looking at, or where did that come from?
Ooh, this actually came from a number of lads. This came from Voigt a couple of years before Einstein, and then there was Lorentz, who used this for his stationary ether theory, where the contraction would be rigid bodies moving through a stationary ether would contract proportional as a function of the square of their velocity over c squared. Now, you might be thinking, well, wait a minute. Didn't relativity remove the ether but keep the same mechanism? Oh no, there's no distinction between these? Oh, okay, cool. So it's literally just interjecting partial derivatives for time to explain everything. So if you break everything, if you say there's no absolute time, you can just break everything into small sections of time, like where everything has to be relative to something else, and we don't have a complete coherent picture for invariance. We can only have covariance.
Quick question.
Yeah, go ahead.
Are you saying that rather than accepting that the speed of light had been modified to slightly higher or lower values through their measurements, they just said that the speed of light is actually more constant than the fabric of space, time, and reality itself?
Yes,
And we just
sir.
bend those instead?
Yes, sir.
Cool.
And because they bend it at an accepted predictable rate, it's okay. It's part of the theory, Brody.
Thanks.
Yeah. So yeah, all they had to do to get people to accept that was just really have you never like if you look at the measurements for what they are at the first order, right? They measured a velocity of 6 to 8 kilometers a second, but that goes outside of the confines of Kepler's laws and all that for how they applied everything to the sky and how they were using C as a ratio for stellar aberration and whatnot. So it was really important for them that C be the same. It can't just be measured differently without supporting the heliocentric velocity, because if it supports a different velocity, that throws all their dynamics off. So it became extremely important to make C a constant, because then you have an infinite yardstick that you could apply to everything in the sky. All right, so when we're looking at the transfer for Lorentz transformations as the square of the velocity, you get these hyperbolic curves here. So just as you're going faster, you're going to get more curvature. That's all this really represents here, just to show you what that looks like. So we got the time, the world line, your time axis. You got your x-axis, your direction of motion. Your contraction will happen in the direction of motion, and your time will also dilate, in correspondence with that velocity. And the deviation between the two is represented by this graph. Very simple and straightforward. So it's these link contraction, time dilation. What this would look like when you fill in the velocities for everything. This is what the deviations would look like with respect to an inertial observer, and then the moving observer would have a deviation in time and proper length based on the square of their velocity. All right, and then we get into Einstein's field equations for general relativity, because it wasn't enough to just say that, well, you can't measure relative motion in that way. They actually had to change orbital parameters again and say that we're actually on a geodesic and we're free falling through a gravitational well, which is represented by this right here. And here we have the gravitational constant, which is just distributing the mass and energy and momentum conservation that's turned into a gravitational field. So this distributes that over space. And then these bad boys over here are the space-time coordinate systems. That curve corresponding to this distribution of the gravitational field in 8 pi g over 4, or over c to the fourth.
Wait, so
this is maxed out covariance at this point, right? So this is like full abandonment of first order measurements. This is now making it about covariant, like just it's the most egregious amount of coordinate system manipulation you could do to keep the speed of light the same, to try and use it as that yardstick, right? And we'll get into the issues with that, with covariance and invariant transformations here in a second. Did you have a question, sir?
Yeah, I was gonna on the last slide there. Is the left-hand side of that equation a complete fabrication with a coordinate system without a datum called space-time curvature? So you're equating something in reality to something not based in reality, like literally math, number lines, Cartesian, and mathematical nonsense land. Just like
That's exactly what this is.
okay, all right, because
That's exactly what this is. Not this guy here, not the lambda. The lambda here,
yep.
right? This is a special case for when you want to describe the whole universe. And you need some dark matter and dark energy to bend and curve space-time. You hit it with this.
Nice.
But the G, yeah, these right here, like this G mu nu, G mu nu and big G mu nu, these are coordinates that have no datum associated with it and represent nothing in reality.
Excellent. Thank you. That's my only question.
Yes. We'll get into covariant and invariant transformations. So earlier I talked about Galilean invariance and Maxwell's equations and the big problem with that and some partial time derivatives that Einstein introduced. It was found by Hertz that if you use a total time derivative, or I'm sorry, absolute derivative to establish absolute time, and then you take derivatives of that for the moving frame, you can have first order invariance for all of the equations for all of Maxwell's field equations. So describe the density and current density of a electric and magnetic field and all that. All of that can be restored with first order invariance, but you would destroy the space-time symmetry, which is built upon the idea of covariance. Yes. Oh.
Even if everybody else is sitting.
Is that a person or?
I think it was a hot.
And he's gone. It was Methuselah.
Okay. Cool. Okay. Yeah. So yeah, the math is a little more rigorous, but it gives you first order invariance, which is a fancy way of saying we're accurately representing reality as is, and we're not overlaying a mathematical abstraction over it to create a false story of how we think it could be. And that's where you get into the second order stuff. So what Hertz found and what Thomas Phipps found when he continued Hertz's work was that when you use absolute time and then you take derivatives of that for the moving frame, you're left over with a velocity component. And what that turned into was the velocity of the detector. So just by using absolute time, right, instead of saying that there's no absolute time, everything worked out exactly as it should to represent reality, with no issues, with no second order transformations, no link contracting, no time dilating, just everything as is.
Yeah, but it's too late when you already know length contracts and time dilates, isn't it?
Yep. And there was one more thing I wanted to add to that, but it just slipped my mind.
My bad.
Oh, you're good. It wasn't you. It happened right before. So it was already coming anyway, or it was already gone. So the equations are accepted from Maxwell. Let us see the free space. So yeah, he goes through the math and does the easiest forms of the transformations, setting everything to free space, and goes through and shows that you can, using the absolute time and derivatives of that and that velocity component, you can fully describe all of Maxwell's equations. Conclusion. Let's see. Oh, that was in relation to something else. So yeah, we'll read a quick thing here on invariance and covariance. I'm sorry, we'll read a quick thing here on covariance that was put forward by Æther, and some Russian lad that was in the same paper as Galev. So see here, it says, let's consider the general claims of general relativity theory. We begin with the myth of covariance. The unambiguous solution of any differential equation is determined except form of the equation also by specification of the initial and or boundary conditions. If they are not specified, then in the general case, the covariance does nothing to determine anything, or at changing the character of the solution can even result in physical nonsense. If, however, the initial and or boundary conditions are specified, Then with the substitution of the solutions, we obtain the identities which remain to be identities in any case for the correct transformation. For the solution, it is possible to invent equations which will be invariant with respect to some specified transformation if we properly interchange the initial and or boundary conditions. The analogies of subspace are often used in the general theory or general relativity theory. For example, a flat rolled sheet is considered. However, the subspace cannot be considered separately from the space as a whole. For example, in rolling a sheet into a cylinder, the researcher usually transfers for convenience into the cylindrical coordinate system. However, this mathematical manipulation does not influence at all the real three-dimensional space and the shortest real distance. There you have it. That's so what Shane was talking about earlier, with those metrics and being able to swap them in, because there's more than just one space-time metric that you can use. You can use flat space-time, you can use curved space-time. Oh, suppose you want to change another condition. Suppose you want to change how the conservation laws are interpreted. Well, you can use your your Lindau-Lifshitz-Fitzgerald energy tensor to describe the conservation laws with that, or you could use Einstein's pseudo-tensor, or you could use some other tensor that somebody else derived that will give you that specified transformation that will give you covariance, right?
And if some other
And-
time it doesn't match, there'll be a new tensor and it will match. So don't you worry.
Yep. And to just kind of show the ridiculousness of it, with the what do they call it? The correspondence principle, right? So like your new theory should be able to explain all the stuff of the old theory, and then whatever else the old theory couldn't explain. So people were complaining that they couldn't do that. The theory wasn't reducing back to Newtonian's approximation. So he was like, "No worries, lads. We can just take a partial derivative of the space-time coordinate system. So something that you can already make infinitesimally flat." He was like, "We'll just take a partial of that and make it even flatter, and then we can Newtonian our way out of here. No worries, lads." And everyone was like, "Oh, hand claps all around. Woo."
Yeah, I think
So that's all. Yeah, go ahead.
just real quick, I think for some people, if you are at all familiar with like computer science concepts or anything, I think I like to talk about it as like code frameworks. And it's like you can get really, really bad code, and then instead of actually rewriting the code and figuring out why it's so bad and why it's like not how it should be, instead of doing that, you can write more code to make the mess that you've created work or do what you want it to do, right? But like you're never actually going back to your code base and fixing the actual problem. And that's like, and then let's say that the abstraction layer you added on top of your code base to fix the bad code base doesn't solve your problem anymore. Well, you still don't have to fix your code base because you can put another abstraction layer on top of that. And you've got really bad, slow, cumbersome code at this point, but you don't care because it's working or whatever. That's kind of what I see with this to an extent, but it's like even more meaningless. So it's almost not even a great analogy. But like it's just like to me, it makes sense because it's the code is kind of like our way of trying to explain things, right? And like instead of ever going back and looking at their original explanation and going back to classical mechanics and seeing how they were wrong when they said that classical mechanics were wrong, instead of going back to that, they just keep adding layers and layers of abstraction. And when you add these partial derivatives in like this, and you you throw infinity in there, like you are giving yourself that room every time they throw in these derivatives or these partial derivatives. They give themselves this infinite room to now do whatever they want mathematically to make their old explanation make sense again. So I don't know if that helped anybody, but that's kind of for me how I've always kind of conceptualized it.
No, that's exactly what happened, man. So it started with Maxwell's equations to describe electromagnetism, and when they ran into a situation where it didn't go their way, they were like, well, what do we do now? Because if we do anything other than second order transformations and follow this Lorentz stuff, the implication is that the Earth is stationary or moving really, really slow compared to what we thought.
Yeah, it's all built to abstract that away, essentially.
Yeah, and they had to keep building over top of that. And here we're reading from Einstein's 1915 paper for the general theory, but he's throwing a shout out to the boys here. He's saying Just as the special theory of relativity is based upon the postulates that all the equations have to be covariant relative to linear orthogonal transformations, so the theory developed here rests upon the postulate of covariance of all systems of equations relative to transformation with the substitution determinant 1. Nobody who really grasped it escaped from its charm because it signifies the real triumph of general differential calculus as founded by Gauss, Riemann, Christoph, Ricci, and Levi Civita. So he's like, earlier we talked about Lorentz covariance and how you can establish C as an invariant through making predicted changes in the coordinate system, time and space as a square of the function, or as a function of the square of the velocity over C squared. And then he's like, yeah, the people who really get that, you got to check this out. He was like, you guys like abstractions? Check your boy out. So, I mean, that's really all it is there. So, and that gives way to this right here.
Oh, gross.
This is where they play the bending and warping of the fabric of a coordinate system.
Oh, look, the cause of gravity right there. Wow,
Right.
look how beautiful.
Oh, look at that, Shane. If you zoom in there, you'll see this datum's associated with not a goddarn thing.
And this theoretical framework of nothing where these two balls play, that's where gravity comes from. I get it.
All right, boys. We have a light in the sky here on the right. We have a light in the sky here on the left. And there's a periodicity of their motion as we're watching them. These lights flicker in the sky. So we're going to apply that periodicity to this nonsense. And suddenly, the fabric, right, of this coordinate system is bending to describe the motion.
It's a big game of Emperor Wears No Clothes, right? It's like everyone wants to get it. They're like, oh, you just don't get it.
Hey, baby, watch this.
Oh, you're hot, Mike and JT. Oh, yeah. Because there's nothing physically tangible about this.
Not a single thing.
No tie to reality whatsoever cannot be overstated enough.
Yep. This is how you math it. Cool.
This is how you math it. Yeah. Purely math and Cartesian. Like, it's like you took a number line, you put it in 3D space, you played make believe, you closed your eyes, boom, out came space time curvature funded gravity.
Yep. Cool. Neat, guys. No
That's
causal
pretty much-
mechanisms, but that was a cool math.
Yeah. Oh, yeah. Well, so what happened? Oh, yeah. These bodies, dude, the space in between them is folding.
At a rate which is predictable based on Einsteinian field equation, which measures the curvature therein. Boom.
Yeah. It gets wild out there. And then when you get into something like when you do a dimensional analysis of relativity, like Stephen Crothers did, you'll find that these pseudo tensors that they're using for their to put the conservation laws into a gravitational field to even start doing all this stuff, it's not even physically meaningful in their own covariant role play.
Yeah,
Because
dude,
because the metrics aren't even derived in whatever meaningful way that they're supposed to be to give an actual ordered structure to the math. It's just completely violated for there to even be just so they can have a tensor to put something there so that they can start to even do the math. The whole thing's a charade.
man, this part got so wrapped in mysticism and just like pseudoscience that people were scared to question it. And I just wanted to say that this is retarded. It's retarded all the way through. You're not supposed to understand it. If you do, if you just like put off your understanding, other smarter people get this. That's incorrect. Okay.
Nah, you just don't get it, Shane.
So
Like,
What's up?
so think about this. A scalar number is just a point. Okay, it's like a zero-dimensional thing. A vector number is like one-dimensional. Okay, it has a size because it's like a line, right? A matrix is like a grid of vectors. It's like a two-dimensional, and a tensor is like a bunch of it's like a bunch of matrices stacked on top of each other, so it becomes three-dimensional. So a vector's like 1, and then a matrix is like 2D, and then a tensor is like 3D. It's just a number space. It's not like you can make a tensor describing whatever you want to. They're making a tensor to describe the curvature of the fabric of nothingness.
of other numbers
Space.
in land.
No,
Yeah, exactly.
No, of empty space. The curvature of empty space, which is nothingness. So they're curving nothing.
Or you mean like in the reality that they're trying to describe? Because in the
Yeah.
math, they're just using that to describe other math, which is
Yeah, they're assigning like they're taking the values, like let's just say like within this region of empty space you have like energy measured or there's mass present or whatever's present. Like the tensor is going to hold the values for whatever measurements you're taking. And then they say, okay, we put parentheses around the tensor and then we multiply it or divide it by some factor and we just shrank it. Oh, and that factor, by the way, is going to be related to a ratio of the speed of light.
Amongst the other things we can't falsify, we're also going to add how, oh, geez, I had it on the tip of my tongue, that we're also going to be, I'll get back to you, a measurement.
No worries, lad. Yeah, just to kind of add on what Pizio was saying, you can make you can use tensor calculus and differential geometry to describe anything. So say you're an engineer and you want to describe the dimensions of an I-beam and you want to describe how much pressure is going to be exerted on it at some point during its its use or whatever, and temperature and all that, and how that's going to relate to different points on it. So you would just use tensor calculus to do exactly that. That's like, it does have practical use, right? But it's like how they're applying it. So like the point that Shane was bringing up, it's like they're just applying it to nothing. It's just space time. It's not a real thing. Has not associated with anything physical or anything that you could manipulate yourself or do anything with. Just pure mathematical abstraction taken to the limit, right? So like the dimensions of space and time, I think it's, what is it? It's the speed of light times t, so it's just infinity, and then speed of light times x for the for the dimensions, which is just infinity again. They just got a big blank infinity, and then when they need to describe something within it, they're just like, okay, we're just going to look at an infinitesimally flat part of space time between these two, and we'll look at the gravitational influence between them in relation to one another. That's all it is.
Don't they multiply? They take the Lorentz factor, plug in the velocity or the mass if they do the mass version, and then just multiply the entire tensor by that factor. And it's like, oh, here's how much it warped by.
I'm not sure.
essentially.
It was
Oh.
yeah. Talking about for gravitational mass.
Yeah, I'm talking about like when stuff moves, like they say, like close to the speed of light, the closer to the speed of light you get, the greater of Lorentz factor you get that you have to account for the length contraction time dilation it'll undergo.
Yes.
Give me back to this one over here or whatever.
Hey, can I ask a clarifying question real quick in regards to what Toby had said? So the way I'm kind of imagining this in my head is more like an applied science or health science, where I go to a doctor with an issue, and he, rather than finding out what's wrong, he just gives me a medication for the symptom. And then that medication ends up causing a whole bunch more symptoms. And so I go back to the doctor, and rather than finding the root of the problem, he just continues to now give me more medication to now deal with the side effects of the initial medication, right? So I'm being put on more and more medication. I'm trying to paint this picture of like how I think Toby kind of described it with the
Never addressing the root.
It's never
the
addressing
root cause.
Yeah.
FaceTime devotee over here.
Meanwhile, I'm just getting put on more and more medications to try and deal with the symptoms that the medications caused in the first place. Is that kind of what I'm gathering out of this?
Yep. And then JT's mic's lighting up. But if you were to go back to your doctor and say, "Hey, doc, I don't believe these medications are helping me," then the doctor would go, "Oh, well, you know what? It's just because you're not smart enough to understand it."
That's such a good analogy.
Really, it happens like that all the time. Or they'll say it in like jargon, scientific jargon that you don't understand, and then scoff at you because you don't get it.
No, what he'll say is, "Are you sure you're taking it in the morning?" And I'm like, "Yeah, right in the morning." And he's like, "Well, okay, maybe try taking it at night. And then I'll give you this other one to deal with the fact that it keeps you up all night. So this one should make you sleepy, and this one will keep you awake." And meanwhile, I'm just on all these medications.
Covariance, exactly.
And
it is very
the
similar
whole time,
to that.
Yeah, and I still have a runny nose, and that's why I went in the first place. It's ridiculous.
Pretty close. Anyone else have any questions, comments?
No, sir.
I would just say on top of that, it makes sense why we see this in all of sciences, whether it's health science or, I mean, it's not really surprising, because I think this has been the foundation of applied sciences. It's just like with solar panels, kind of like I use solar panels as an example. Sure, we know how to build them and make them, but we have no clue how they work, and we'll make up stories about how they work. But like if you ask someone who actually works in them, they don't understand how they. And it's like the foundation of science seems to be just a bunch of made up jargon, whether it's health and medicine, whether it's applied sciences, physics. I don't know. This isn't surprising to hear, is what I'm saying.
Yeah. And so like if you were to go back and so like what would happen if you re-examined everything and went back to the source of the issue, like our boy Phipps did here? Where he introduced absolute time and then partial derivatives for the moving frame, and then it gives you the velocity component, which magically explains everything with first order invariance, which is just a fancy way of saying it accurately represents reality as is without making things up, right? So that's why you can't go back and re-examine it at this point, because everything that was built upon ignoring this issue would collapse, and that's all Einstein's theory is built upon. False conjecture and a belief in a velocity component that's never been measured.
Steadfast, aggressive belief in that velocity component, mind you.
Yeah, strict adherence to it, dog. Dude, they threw out measurements that they took in the lab because they believed that the velocities would be much, or like, bro, you travel much faster than that around nebula. These velocities are these are DS. This is an air.
Man, I'm still trying
They're defective, dude.
They're defective, man.
Wrap my head around how the dynamic cause of gravity actually exists in fairyland and nothing to do with reality. Like the way that reality works is that it exists only not in reality.
It's like, oh, dude, at the local scale, bro, it's all Newton and mass attracting mass.
The curvature of space-time is doing.
And then it's like, but what it actually is, though, like on that real grind, like now that you're a graduated Illuminati 33rd degree doctorate, we'll tell you how gravity really works. Like, you know how we were on that mass attract mass grind? Nah, dude, that ain't it at all, homie. Reality bends to the mass.
It
makes distances shorter.
And that's what causes gravity. That is downright amazingly retarded.
Yeah. And then all supplemented by pictures from space, right? This is the only reason people believe in any of this.
Mass attracting mass is less retarded than this, honestly.
You could only get here by space images to confirm this stuff, because this is the only thing.
Normies only.
Yeah, this is the only thing that would give you like mutual exclusivity over causal mechanisms. I mean, think of the balls you would have to say without being able to leave this system, look another man dead in his oculars and say reality bends in an imperceptible way around him.
Well, listen, unless you could deconstruct one of them tensors right there, then I'm believing the smart guy. You're a fucking idiot. Like, that's how they got everyone.
Yeah.
I have a comment. I hate to break it to you, but my cell phone works. Therefore, all of the science is right.
Now she's getting
and you guys are wrong because my cell phone works. I swear to God, I had a Globee tell me that one time.
Yeah, I think we've all heard it more than once.
I think we all spoke to that Globee.
Those guys make me smile.
Oh, that shit's cute though, because it's like, oh, you don't know nothing, huh?
It's like, you just started. Okay.
Yeah, you just woke up, huh?
in all seriousness, it just is mind blowing that the emperor wears no clothes. It's like nobody is talking about it.
Well, if you imagine you were given instant status and like reverence for saying that the emperor does in fact have clothes,
Right, like imagine
Despite
the
the fact that
amount of money you get is directly related to how embellishing you get with the description of the lack of emperor's clothes you can put out, right? Like if you were really good at it, you got tons of money. So
Strictly restricted to whispers down the hall you might hear.
that's a really
But
great
also,
analogy.
if you do say something, and then it's off with your head, you know.
It's like literally
So
Plato's allegory of the
Hence my
cave.
comment.
You only make money when you can really describe and name those shadows with eloquence and specificity, right? Otherwise, you don't make any money. It's all about naming shadows, boys.
Well, to me, these sessions that you guys hold, the readings, this is really basically just bringing the whole temple down one brick at a time,
very methodically so.
I think it's Alan's life mission. Yeah, I was just thinking. I think that's like his life goal is to bring down the temple one by one. I think he was given a vision or something. I don't know.
Yo, sorry about the hot mic earlier. I was gonna say, Alan, I listened to your stream. It was like your video on the same thing earlier, and I was driving by myself, and I was just saying out loud, trying to like understand the difference between kinematics and dynamics. And I was like, oh, Ken throws the ball. So I gave kinematics like a character named Ken, and he's chunking the ball, and it's coming at my face, and all I care about is kind of like eyeballing the trajectory and kind of when it's going to come over so I can catch it, but it has nothing to do with like how strong he was, how much force he put into the ball, wind resistance, or none of that. That's all dynamics. And I know it's like a no-brainer, but as somebody's learning, I really appreciate your videos and the way that you break it down with humor, and you just make it clear so it sticks in my head. So appreciate it.
Nice, dude. Glad that was able to stick because that's the most fundamental, important part of physics, the distinction between kinematics and dynamics. And
Yeah.
seeing the just when you see them the conflation happen, you're like, ooh, like it makes sense now, like why these things are the way they are and why people believe in them as like dynamics because they don't understand or weren't properly taught the how to distinguish between the two, and there's for good
How
reason for that,
easily.
right?
Almost on purpose.
Yes.
it seems, yeah.
How easily the wool is pulled.
Yep.
I think a wise man
Wow.
once said that that's the biggest problem in physics, that they don't actually tell you how to differentiate, and they specifically like make them like conflate them together, like on purpose almost.
Wouldn't they
So
have to be all in on it?
basically, as you're looking at the emperor's junk, someone's telling you, no, that's his tassel on underwear, dude. And you're like, no, I'm pretty sure that's a full-blown junk right there. He's like, no.
Well, it's reference frame dependent, I guess, but yeah.
The elongation of the curvature of the junk is actually dependent on the system in which it's represented, which is actually invariant between coordinate system transforms as it happens. Cartesian simultaneity. Who was that talking about the cylindrical part of it? It was like actually when we project it, and it's the same distance because we exist in Cartesian simultaneity. Cylindrical is just one variant of the expression that we can do for the actual distance in the coordinate system, right? I dug that part. I like this presentation. One of my favorites. Although I think everyone needs to do another round of how math became reality, because this leads right into that. It's like, how did math become reality? Oh, well, people believe this shit. You know how we just went right through it? It's like, this is how you make math your reality. These steps, just follow this guide.
Yep. Once you get high on your own math, I mean, there's really no turning back.
Or he can get, I think it's like, you can get high in Einstein's math. That's all you take, right? A good old like community high. You all get high together on Einstein. That's even better with friends.
With friends. Solving differential equations with the boys to get high on math. Nice.
Like it's only fun with friends. Otherwise, you're just a nerd doing relativistic equations by yourself.
All right. Well, I think that wraps up the prez. If there's no further questionings or if anyone wants to add anything. See Cassandra out there in the streets. I know you got some kinematic and dynamic gravy. Want to add anything before we close up?
sounded like a start of a yes.
We heard the mic go off, but nothing came out.
Yeah, got to get more comfy with your microphone.
Did you?
You gotta have the
There it is.
you gotta have
Yeah,
the
you gotta bring it on
microphone in the
down.
down position.
That's right.
Yeah, I thought, Alan, that you had presented this before. That you had a video on this topic that I saw before.
Yep. Wanted to do it live.
Yeah.
Yep. Yes, people were still asking about it and stuff. So
Worth a refresher.
Yeah, very crucial topic, worth hammering in.
it's my favorite subject. Distinction between the two.
Did you publish a video before, Alan,
Yes.
on this topic, right?
Yep. A couple days ago.
Yeah. Okay. Well, I agree with the kinematics and dynamics definition, but the covariance and invariance, I think Mr. Norton at University of Pittsburgh would have some objections.
Oh yeah, it was old Norton.
Yeah, that's a good reference for you and Shane. The topic of general relativity and covariance. Invariance means that an object doesn't change its value when you change coordinate systems. An example of that would be mass. Mass is the same in whatever coordinate system you choose. Covariance means that the form of an equation stays the same. You change coordinate systems. Norton points out that covariance has two types. If you make a coordinate system change, which means, for example, change from Cartesian coordinates to polar coordinates or spherical coordinates, it's just a mathematical change. And so to say that something has covariance under coordinate transformations is an empty statement. I mean, that's obvious from the fact that you're just changing the grid that you're placing on reality, but that you're changing the mathematic description, but that doesn't change the physical reality of whatever you're measuring. However, if you do a Galilean transformation, then you have a different situation. You don't have a coordinate system, you have a reference system. A reference system includes an observer, clock, ruler, everything you need in order to make measurements. And when you have that situation, for example, when you change from an observer on the Earth to someone in a satellite or on the moon or in any other reference system, and you use the term reference system to distinguish the fact that you're not doing a mathematical change, doing a physical change, because this is mapped into reality. When you just change a coordinate system, just changing the map that you're putting on the physical reality. So covariance has two types. The empty type, which is coordinate system covariance, and then the other type of covariance is the one we're really interested in. That's the one that leaves the form of the equations unchanged. So if you have F equals ma in, let's say, the Earth reference frame, and you ask, what would that equation B if you did the observations from the moon observer? So the question that that basic answer was given by Newton's bucket, which says that the true equation is given in the Earth's reference frame, because that gives the correct results. It does predict that the bucket water would form a vortex when you have a rotation with respect to the Earth system. With respect to the moon system or any other system, you get a different result, and it won't agree with reality. So covariance is a topic which is kind of forced aside. I do agree with the comments that most of you made about the fact that mathematicians have taken over physics, and they actually, Einstein had to resort to going to mathematicians in order to come up with general relativity. You can read about that. In the period from 1905 to 1915, he worked with mathematicians to produce, as most of you said correctly, most of you said correctly, the mathematics is what's driving modern physics and not experimentation. I've got to take care of some business here, but if you have any questions, you can bring them up on Discord, and I have to close it out now. You can probably hear the background noise.
No worries. Much appreciated, man. Thanks for adding that.
Hey, Cassandra,
Yeah,
stay on after this presentation's over. When it's over, we all stay on and talk afterwards. Just to let you know, I don't know if we
Right.
do that, but
Well, tonight it
stay on the
sounds like
call.
he's got to go.
Yeah, I'd like to,
Yeah.
but I'm not sure I can.
I just want to say I love his profile pic. If you guys didn't notice, it's a hook on a giant stick looking for truth. I just realized that. Did you make that? Did he find that? Did you guys help him with that?
He's gone.
Oh.
All right, got a bit.
Later.
Nice. Well, that was great, man. Thanks, Alan.
Yeah, no, dude, that's a very important distinction too about the coordinate system with an observer. When that's now a reference frame, like that invokes an observer versus a coordinate system, which is just pure abstraction.
Coordinate versus reference system. Yeah.
Sir.
I'm pretty sure that's a hangman's noose and not a hook.
Yeah,
Right?
It's a gallows.
Yeah, it is. It's that. So is
That's
he hanging the
yeah.
truth? Tell me that.
No, he's here to hang you with the truth.
Okay. All right.
Yeah,
That.
the rope of truth is here to, well, take your life.
Or is he giving you enough rope for you to hang yourself with the truth?
Yeah. All right.
Yep.
I'm gonna. So speaking of hanging ropes and truth, does anyone know where I can get some coffee? I'm so thirsty right now.
Well, yeah, I certainly do there, Alan. I'm so glad you asked. As a matter of fact, if you want to drink the best fresh roasted coffee roasted by yours truly, you can head on over to brushtail.coffee. That is BRUSHTAIL.COFFEE or brushtailcoffee.com. Head on over there and you can order coffee there. You can also subscribe there. I roasted myself in my garage on a special, essentially just a grill with a special rotating drums configuration. It's always roasted fresh and shipped fresh, and for that reason, it's the best. Also, I just happen to have like the best coffee palate, so you're just always going to get the best coffee. So, bim, bam, bada, boom. Can't beat it. Brushtail.coffee. Yeah, there you go.
Brushtail out.
Brushtail out. Everyone, thanks for listening in. Thanks everyone for listening in tonight. Alan, fantastic presentation. We have indeed talked about this numerous times, and you have given numerous presentations that have covered quite explicitly this topic. But you know, a lot of topics really really are worth repeating, especially like this, where it's so fundamental to understanding where physics has gone. Like we kind of have to talk about this all the time because, you know, what's the point of talking about relativity? Really, this is the only point, right? Like this is all it really comes down to. Like there's no point in going any deeper than this, to an extent, because we have to really just hammer home the fact that, you know, these are all backwards derived equations. These are all derived to explain what we have observed. It's not, they're not taking dynamics and then, you know, putting those all together and having like a cohesive framework of like unified theories where everything is, you know, is explicitly, where you can explain everything and everything has its own properties and its own, you know, attributes. That's not what's going on. This is backwards derived stuff that, you know, kinematics. It's descriptions of the observed motions. It's not the how. And so, really, it's impressive. Sure, you can math it, cool, but it's utterly meaningless as far as explaining how the universe is working. And to try and use it to assert that is very fallacious, and that's what modern physics does. And that's why when you see these Sean Carroll types and these dorks like Michio Kaku and stuff, that's why it sounds like they're just, you know, like just esoteric gibberish, because that's what it is. We have modern physics has detached itself from reality. So, you know, have fun with that if you're into it. But we're over here we're trying to figure out what was being discussed before things took this crazy turn. And it looks like there's a medium that everything's in. So that's what we do here. So yeah, thanks again, everybody. Take care.